NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
In a new world-shattering revelation, the James Webb Telescope has delivered the unthinkable: evidence of life on Proxima b, an exoplanet orbiting the closest star to the Sun. This discovery is nothing short of groundbreaking, representing humanity's first confirmation of life beyond Earth. What began as a promising observation of this rocky world has transformed into one of the most profound revelations in human history, a discovery that will undoubtedly alter our understanding of life's potential across the cosmos. Join us in today's episode as we dig deep into the latest stunning observations of Proxima b and how it could change everything we know about the universe. As shocking as it sounds, we find exoplanets, or planets orbiting stars other than our Sun, all the time now. We know of nearly 6,000 such planets plus another 10,000 planet candidates. So what makes Proxima b so particularly exciting? First off, Proxima b is roughly 4.2 light-years away, orbiting its red dwarf host star Proxima Centauri, the closest star to the Sun. This close proximity allows astronomers to study it in ways that are simply impossible with more distant exoplanets. Its mass is nearly identical to Earth's, at about 1.17 times that of our planet, and its size is also comparable. Proxima b completes an orbit around its star in a mere 11.2 days, remarkably fast compared to Earth's 365-day orbit. But since Proxima Centauri is a red dwarf, it's a much smaller and cooler star than our Sun. This means that even though Proxima b is incredibly close to its star, it still falls within Proxima Centauri's habitable zone, a range where conditions might be just right for liquid water to exist. This delicate balance of distance and temperature could, in theory, allow Proxima Centauri b to have water on its surface, a fundamental ingredient for life as we know it. The planet receives a similar amount of solar energy from its star as Earth does from the Sun, further supporting the possibility of a temperate environment. However, while this arrangement sounds ideal, several factors must be considered before we can truly assess Proxima b's habitability. Habitability on any planet depends on an interplay of various factors, including surface temperature, atmospheric composition, water availability, and the levels of radiation from its star. One of the most significant challenges Proxima Centauri b faces is the environment created by its red dwarf star. Red dwarfs are notorious for emitting intense stellar flares, bursts of energy and radiation that can bathe nearby planets in harmful radiation. These flares could strip away Proxima b's atmosphere over time, especially if the planet lacks a strong magnetic field to shield itself. For Proxima Centauri b, radiation levels may be quite different from those on Earth, adding complexity to the question of habitability. What further complicates matters is that the usual methods we rely on to detect biosignatures, or signs of life, don't work well with Proxima Centauri b. Most exoplanets are discovered using the transit method. This method involves observing a planet as it passes directly in front of its star from our perspective, causing a temporary dip in the star's brightness. These transit events also allow astronomers to analyze the star's light as it filters through the planet's atmosphere, revealing the presence of certain molecules. By studying the wavelengths of light that get absorbed as the planet transits, scientists can identify various gases, such as water vapor, carbon dioxide, or methane, that may hint at life. However, Proxima Centauri b doesn't transit its star from our vantage point, so we can't directly study its atmosphere this way. Instead, Proxima Centauri b was discovered using a different approach known as Doppler spectroscopy, or the Wobble method. This method detects slight shifts in the star's spectrum as it moves towards and away from Earth, influenced by the gravitational tug of Proxima Centauri b as it orbits. Through Doppler spectroscopy, we can deduce details like the planet's mass and orbital period, but without transits, analyzing its atmosphere remains challenging. Despite these hurdles, astronomers are exploring alternative methods that may allow us to detect signs of life on Proxima Centauri b. One intriguing possibility lies in observing artificial light on the planet's night side. Imagine looking at Earth from a distant vantage point in space. The most conspicuous indicator of life on the planet at night would be the glow of artificial lights from cities. In principle, if a civilization on Proxima Centauri b were using artificial illumination, we might be able to detect it by analyzing the reflected light from its night side. For example, the kind of artificial light used by human civilizations, such as LEDs, has a specific spectrum. Theoretically, similar illumination from Proxima Centauri b could appear in telescope observations as an unusual reflection pattern, distinguishable from natural light sources. While challenging, this method has been used in our own solar system to observe planets that don't transit the sun. By analyzing the reflective light of these worlds, we can infer surface features and, potentially, even detect artificial illumination. Detecting the reflected light from Proxima Centauri b would be a remarkable achievement. Given that this light would be minuscule compared to the brightness of its star, it's akin to spotting a firefly near a searchlight. However, advancements in telescope technology have opened up possibilities that were unimaginable even a decade ago. The James Webb Space Telescope, along with its highly sensitive infrared detectors, is well suited to observe faint reflections from exoplanets like Proxima Centauri b. Webb's capabilities are revolutionary. The telescope's large, precision-crafted mirrors gather and focus light from distant objects, channeling it through various filters and spectroscopic tools to detect faint infrared signals. These innovations enable James Webb to capture data from far-off planets and stars with unprecedented accuracy. As such, the telescope could potentially pick up on dim, artificial illumination on Proxima Centauri b's night side. Astronomers have modeled artificial illumination as a percentage of the solar illumination reflecting from the planet's day side, with 0% indicating no artificial light and 100% suggesting a brightness equal to daylight. If Proxima Centauri b's night side illumination reached just 5% of its dayside brightness, the James Webb could detect this with about 85% certainty, and at 9%, the detection confidence would rise to 95%. In recent observations, the Webb telescope has directed its powerful sensors toward Proxima Centauri b, yielding data that scientists are eager to analyze. Initial findings indicated that the planet's atmosphere contained a curious mix of gases that are strongly associated with biological processes on Earth. Spectroscopic analysis revealed not only the presence of water vapor, which suggests that liquid water may exist on the planet's surface, but also an intriguing balance of oxygen, carbon dioxide, and methane. This combination of gases is what scientists refer to as a biosignature, an atmospheric signature that strongly suggests biological activity. Methane, in particular, is a key indicator because it breaks down quickly in the presence of oxygen, meaning that something must be replenishing it. On Earth, this replenishment is primarily done by living organisms, especially microorganisms. While methane can be produced by volcanic activity or chemical reactions, the ratios of gases on Proxima b are far more consistent with biological processes than with abiotic ones. James Webb's instruments were able to detect a steady, ongoing production of methane and oxygen, which points to the existence of a stable ecosystem. In addition, trace amounts of nitrous oxide, a gas often produced by bacteria on Earth, were also found, adding further weight to the hypothesis that life exists on the planet. While atmospheric biosignatures provide compelling evidence, the observations made by James Webb have gone further, hinting at the possibility of a surface teeming with life. Through the telescope's highly sensitive infrared imaging, scientists were able to construct a detailed picture of the planet's surface conditions. What they found was astounding. Proxima b appears to have large areas covered in what could be liquid water, seas, or oceans. Alongside these bodies of water, James Webb has captured what scientists believe are signs of organic pigments, possibly similar to chlorophyll on Earth, which plants use to photosynthesize. These pigments could indicate that simple plant-like organisms are thriving on Proxima b, using the dim light from Proxima Centauri to produce energy. Furthermore, Webb's thermal imaging data suggests that Proxima b experiences significant temperature variations between its day and night sides, as one side of the planet is tidally locked to its star. Despite these harsh conditions, the presence of liquid water and possible photosynthetic life forms suggests that life has adapted to survive in these extremes, much like extremophils do in Earth's most hostile environments. Some researchers have even speculated that more complex life forms could exist on Proxima b. Although no direct evidence of such creatures has been found, the possibility cannot be ruled out. The presence of organic pigments and methane-producing microorganisms could point to a diverse biosphere, where a range of life forms have evolved to occupy different ecological niches. After all, the discovery of sign of life on Proxima b raises profound questions about the origin of life itself. Did life arise independently on this distant world, or was it seeded through a process like panspermia, where life's building blocks are spread throughout the galaxy by comets or meteorites? The answers to these questions could reshape our understanding of biology and the prevalence of life in the universe. Either ways, Proxima Centauri is a red dwarf star, much cooler and dimmer than our Sun. These types of stars are known for their violent stellar flares, which can strip away a planet's atmosphere and make the surface inhospitable. However, Proxima b has somehow retained an atmosphere, suggesting that it may have a strong magnetic field or other protective mechanisms that shield its surface from harmful radiation. The conditions on Proxima b may mirror those of early Earth, where life arose in oceans rich with organic molecules and energy sources like volcanic vents. It's possible that life on Proxima b followed a similar path, developing in water-rich environments where chemical reactions fueled the emergence of simple organisms. The discovery of biological gases like methane and nitrous oxide suggests that microbial life has adapted to Proxima b's unique conditions, possibly leading to a stable ecosystem. If life on Proxima b did indeed arise independently, it would suggest that the universe is teeming with life. Perhaps even that life is a natural outcome when the right conditions are present. Alternatively, if panspermia played a role, it would imply that life's seeds can travel vast distances across space, potentially making life on Earth and Proxima b distant relatives. And of course, such a discovery is more than just a scientific milestone. It is a turning point in human history. For centuries, we have gazed at the stars and wondered if we were alone in the universe. This question has haunted human imagination for thousands of years. Ancient civilizations held beliefs about the stars that were deeply intertwined with their cultures and religions. For the ancient Greeks, the night sky was filled with gods and heroes. Stars and constellations represented mythological figures, and their movements were believed to influence human fate. The philosopher Democritus, one of the first to theorize about the existence of other worlds, suggested that there could be countless stars, some with their own planets and even the potential for other beings. His ideas were radical, and they laid a foundation for considering the possibility of life beyond Earth. In India, the Vedas, a collection of ancient texts, imagined the universe as cyclically created and destroyed by divine forces, spanning immeasurable scales of space and time. Similarly, in Mesoamerican cultures, the cosmos was often represented as a multi-layered world connected by gods and spirits, with the stars serving as the heavenly realm of the ancestors. Ancient Chinese astronomers meticulously observed celestial phenomena, interpreting them as signs that could influence earthly affairs, but also pondering the nature of the stars themselves. Such beliefs reflected an early recognition that the universe is far vaster than what meets the eye, fostering curiosity about other worlds. Across these cultures, however, the question of life beyond Earth lingered, impossible to answer with certainty, but captivating enough to persist. During the Renaissance, revolutionary thinkers like Nicholas Copernicus and Galileo Galilei changed humanity's understanding of the cosmos. Copernicus's heliocentric model, which proposed that the Earth orbited the Sun rather than the other way around, shifted our perspective on our place in the universe. Galileo's telescopic observations revealed that the Moon was not a perfect, ethereal body, but a rocky landscape, much like Earth. Suddenly, celestial bodies were no longer seen as divine realms, but as physical worlds that could, theoretically, host life. This shift in thinking opened the door to a new wave of speculation. Giordano Bruno, an Italian philosopher, was one of the earliest to propose the idea that other stars might have their own planets, which he believed could host other forms of life. Bruno's ideas were so radical for the time that he was executed by the Inquisition, but his writings would inspire future generations of scientists to consider the possibility of a universe teeming with life. The advances of the Renaissance laid the groundwork for modern science, shifting from a worldview in which humanity was the center of creation to one where Earth was merely one planet among many. As telescopes improved, astronomers like Johannes Kepler and Isaac Newton contributed to the understanding that the laws of nature were universal. The realization that other stars operated under the same principles as our own sun was a profound one, suggesting that other planets and possibly life could exist under similar conditions. By the time of the scientific revolution in the 17th and 18th centuries, curiosity about life on other planets had developed from a speculative philosophy into a scientific question. As telescopes became more powerful, astronomers observed features on planets like Mars that seemed to suggest geological activity and even seasonal changes. The Martian canals, popularized in the 19th century by astronomer Giovanni Schiaparelli and later by Percival Lowell, fueled public imagination about the possibility of intelligent Martians constructing vast networks of waterways. These observations sparked a wave of Mars mania, and works like H.G. Wells' The War of the Worlds reflected a popular fascination and fear of alien life. In scientific circles, however, the question of extraterrestrial life remained unanswered. Despite increased understanding of our neighboring planets, the evidence was insufficient to confirm or deny the presence of life. However, the scientific revolution ushered in an era of rigorous astronomical study. William Herschel, the discoverer of Uranus, believed that other planets, including Jupiter and Saturn, might be inhabited. This era of study set the stage for the 20th century, where rapid technological advancements would bring humanity closer to understanding our place in the universe. The launch of Sputnik in 1957 and the subsequent space race marked a turning point in humanity's quest to explore the cosmos. By the 1960s, space exploration had moved beyond Earth's atmosphere, and scientists began to consider the practicalities of finding life beyond our planet. The search for extraterrestrial life shifted from speculation to targeted investigation, with NASA's Viking missions to Mars in the 1970s representing some of the first efforts to directly seek out biological evidence on another world. The 1977 launch of the Voyager probes pushed the boundaries of human exploration even further. Equipped with a golden record containing sounds and images from Earth, the Voyager missions were designed to reach the outer planets and beyond, carrying with them a message to any intelligent life they might encounter. The golden record remains humanity's first interstellar message, a hopeful gesture encapsulating our desire to connect with other beings. During the same period, the scientific community also began efforts to listen for alien signals through projects like SETI, or Search for Extraterrestrial Intelligence. Utilizing radio telescopes, scientists started monitoring the sky for signals that might indicate intelligent life. While no confirmed extraterrestrial signals have been detected, SETI has inspired a range of similar initiatives, leading to an ongoing worldwide effort to scan the cosmos for signs of intelligent communication. In 1995, astronomers discovered the first exoplanet orbiting a sun-like star, 51 Pegasi b, marking a watershed moment in the search for extraterrestrial life. Since then, the discovery of thousands of exoplanets has completely transformed our understanding of the universe. With missions like Kepler, TESS, and most recently, the James Webb Space Telescope, scientists have found that planets are not rare, but incredibly common, with many potentially existing within their star's habitable zones. The future of the search for extraterrestrial life is as exciting as it is uncertain. The solar system has become the heart of this endeavor. Several celestial bodies in our own neighborhood emerge as prime candidates, with Mars, Europa, Enceladus, and Titan leading the way. Mars has captivated the imagination of scientists and the public alike for centuries. This planet has the most Earth-like environment of any in our solar system, which is why it has long been a focus of astrobiological research. Historically, Mars was likely very different from the cold, barren landscape we see today. Geological evidence points to a Mars with rivers, lakes, and perhaps even a vast northern ocean. Although current conditions on Mars are harsh, with a thin atmosphere that cannot retain much heat and high levels of surface radiation, scientists believe there may still be microbial life hiding in more protected environments. Beneath Mars's surface, microbial life might have found a haven in aquifers, regions of rock and soil that hold liquid water. Such subsurface locations offer a potential sanctuary, shielded from the planet's thin atmosphere and solar radiation. These environments may contain conditions conducive to microbial life, with water and possibly other organic compounds that microorganisms would need to survive. The significance of Mars as a potential habitat for life has led to ambitious exploration efforts. Future missions will continue to target Mars in hopes of confirming its habitability. The upcoming Mars Sample Return mission is a collaborative effort between NASA and the ESA that aims to retrieve samples from Mars's surface and bring them back to Earth. By carefully examining these samples, scientists hope to uncover organic molecules or even fossilized microbes, which would be groundbreaking evidence that Mars once supported, or may still support, life. If successful, this mission could fundamentally reshape our understanding of life's prevalence in the universe, with Mars standing as a tantalizing reminder that life might be closer than we ever imagined. Jupiter's icy moon. Europa presents another compelling target for astrobiologists. With an ice-covered surface hiding a vast ocean beneath, Europa holds one of the most promising environments for life in our solar system. Its subsurface ocean, warmed by tidal forces generated by Jupiter's gravity, is thought to have existed for billions of years. This prolonged stability creates an environment where life could theoretically evolve and flourish, shielded from the deadly effects of solar radiation. Europa's subsurface ocean is especially intriguing because it is likely salty, similar to Earth's own oceans, and it may even interact with the rocky seafloor. This interaction could potentially generate hydrothermal vents, which are known to support life on Earth's ocean floor. These underwater environments on Earth are home to ecosystems teeming with unique organisms that thrive without sunlight, using chemical reactions instead of photosynthesis for energy. The possibility of similar vent systems on Europa's seafloor has led scientists to believe that microbial or even complex life could exist in its depths. To explore this icy moon, NASA's Europa Clipper mission, scheduled for launch in the 2020s, will conduct an unprecedented examination of Europa's ice shell and subsurface ocean. By flying multiple times over Europa's surface, the Clipper will search for evidence of life by analyzing the chemical composition of the moon's icy crust and scanning for potential thermal anomalies that could indicate active processes below the ice. Clipper's instruments will also analyze Europa's thin atmosphere for molecules that could be biosignatures. If life is present, or if there are even conditions that resemble a habitable environment, Europa Clipper may well find them. Saturn's moon Enceladus is perhaps one of the most intriguing candidates in the solar system for finding life. Like Europa, Enceladus has a subsurface ocean beneath an icy crust, but what sets it apart are its spectacular geysers. These geysers shoot plumes of water vapor, ice particles, and organic compounds from the moon's interior directly into space, offering a direct glimpse into Enceladus's inner ocean. This phenomenon provides scientists with an extraordinary opportunity to study the ocean's composition without having to drill through the ice. NASA's Cassini spacecraft made flybys of Enceladus in the early 2000s and analyzed the composition of these plumes, detecting organic molecules such as methane. This discovery was remarkable because methane is often associated with biological processes on Earth. While methane can also be produced by non-biological processes, its presence on Enceladus has encouraged astrobiologists to consider that the moon's ocean might host microbial life, or at the very least, conditions conducive to life. Due to these findings, there are now numerous proposals for follow-up missions to Enceladus, each aiming to study its plumes in greater detail. These missions are in various stages of planning, with many scientists advocating for a dedicated life detection mission to explore the plumes more closely. a spacecraft could fly through the plumes, capturing samples and analyzing them for complex organic molecules or even potential biosignatures. With each discovery, Enceladus brings us closer to answering the age-old question of whether life exists beyond Earth. Another fascinating location in the search for life is Saturn's largest moon, Titan. Unlike any other body in our solar system, Titan has a dense atmosphere and surface lakes of liquid methane and ethane. Titan's environment is vastly different from Earth's, with temperatures so cold that water exists as solid ice. However, scientists speculate that life might be able to emerge and thrive in Titan's hydrocarbon lakes, where methane serves as the primary solvent rather than water. Methane-based life, if it exists, would be unlike anything we know on Earth, challenging our assumptions about life's chemistry and what constitutes a habitable environment. On Earth, life is carbon-based and relies on water as a solvent, but Titan presents a unique opportunity to explore the possibility of a different kind of biochemistry. Some scientists believe that organisms on Titan, if they exist, might metabolize hydrogen and acetylene and excrete methane, a reverse of the process seen on Earth. NASA's Dragonfly mission is set to revolutionize our understanding of Titan. Scheduled for the mid-2030s, this rotorcraft mission will explore Titan's dense atmosphere and surface, conducting experiments to analyze the moon's organic molecules and atmospheric composition. Dragonfly will investigate whether the complex chemistry on Titan's surface and in its atmosphere is conducive to life, potentially expanding the definition of what we consider a habitable environment. In addition, as told in recent years, the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has transformed the search for life. Advanced telescopes and observatories are enabling scientists to study these distant worlds in unprecedented detail. The historical launch of James Webb marked a significant leap in the search for life. Its powerful infrared capabilities allow it to study the atmospheres of exoplanets, searching for signs of habitability or even biosignatures. Biosignatures are molecules or patterns in a planet's atmosphere that could indicate biological processes such as oxygen, methane, and water vapor. Webb is currently focusing on planets in the habitable zones of their stars, where conditions may allow for liquid water. Early observations have already yielded promising data, and as James Webb continues its mission, it may identify planets with atmospheres resembling Earth's, where life could potentially exist. And beyond James Webb, new observatories are in development that will enhance our ability to study exoplanets. The Extremely Large Telescope, currently under construction in Chile, will be able to directly image some exoplanets and analyze their atmospheres. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will conduct a survey of exoplanetary systems and search for free-floating planets, expanding our understanding of planet formation and habitability. Moreover, recent discoveries have widened the scope of potential biosignatures, encouraging scientists to consider not only Earth-like molecules, but also exotic chemistries that could indicate life. For example, on planets with a different atmospheric composition, unique combinations of gases, such as methane and carbon dioxide, could suggest biological processes. With an expanding list of potential biosignatures, future telescopes will search for multiple gases and their interactions, aiming to detect patterns that suggest biological activity rather than abiotic processes. While finding microbial life or simple organisms would be groundbreaking, detecting signs of advanced extraterrestrial civilizations or technosignatures would arguably be one of the most profound discoveries in history. Technosignatures are indicators of advanced technology that could suggest the presence of intelligent beings. The CD Institute has been searching for signals from intelligent civilizations for decades, primarily focusing on radio waves. Advances in technology are allowing scientists to broaden their search, incorporating optical signals and even bursts of laser light that could be sent as signals from a distant civilization. In recent years, breakthroughs in machine learning have also enhanced SETI's capabilities, enabling computers to analyze massive amounts of data quickly and detect potential signals that might have been missed by human observers. Besides, a Dyson sphere, a hypothetical structure that could capture a star's energy output, is a popular concept among scientists searching for technosignatures. Although no Dyson spheres have been found, astronomers continue to search for unusual patterns of dimming and brightening in stars that could indicate the presence of such megastructures. Telescopes capable of capturing infrared radiation are particularly valuable in this search, as a Dyson sphere would likely emit excess infrared light. Another technosignature that scientists consider is artificial pollutants. If a planet had significant levels of industrial gases like chlorofluorocarbons in its atmosphere, it might indicate technological activity. Additionally, scientists are exploring the idea of detecting city lights or other artificial illumination on distant planets. With future telescopes such as LIVOIR, also known as Large UV Optical Infrared Surveyor, it might be possible to detect these faint but potentially telling indicators. Last, note that the search for extraterrestrial life is about more than just finding new forms of biology. It's also a profound philosophical endeavor. If we were to discover even microbial life beyond Earth, it would imply that life is not unique to our planet. This would suggest that the universe is filled with the potential for life, challenging many of humanity's long-held beliefs about our place in the cosmos. Furthermore, finding life on another planet would raise ethical questions. How would we treat alien life? Should we make contact if it were intelligent, or would we risk contaminating other ecosystems with our own presence? These are pressing questions, especially if intelligent life were discovered. This discovery would immediately give rise to the ethical considerations that have only been theoretical until now. If life on another planet exists, it would not be enough to marvel at the scientific wonder of it. We would need to consider how we treat these extraterrestrial beings, ensuring that any action taken preserves both their existence and the integrity of their ecosystem. The concept of contact brings with it concerns about contamination. Just as we worry about bringing invasive species into foreign ecosystems on Earth, our presence on a planet that hosts life could have unknown and potentially irreversible effects. We may be driven by a noble curiosity to study these life forms, but what if our attempts to learn result in harmful consequences? The need to approach alien life with respect, caution, and humility becomes paramount, as we have learned from our past mistakes on Earth when invasive species or human interference altered or destroyed native ecosystems. If intelligent extraterrestrial life were discovered, humanity would have to wrestle with its long-standing sense of superiority. For thousands of years, we have lived with the assumption that we are the only beings capable of thought, emotion, and self-awareness. Confronting intelligence from beyond our world would mean seeing ourselves as part of a larger, possibly more complex web of conscious beings in the universe. This discovery could change the way we view concepts of self-awareness, community, and culture, possibly leading to an exchange of knowledge that would deepen our understanding of consciousness itself. In short, whether we find a single-celled microbe or a highly advanced civilization, the sheer knowledge that we are not alone would reshape our understanding of humanity and our place in the universe. To know that life, in whatever form, has managed to take root elsewhere, would prompt us to see ourselves in a new light. Our definition of life would no longer be limited to Earth's unique conditions, opening up new realms of thought about the adaptability and resilience of life itself. It might challenge us to pursue our survival more diligently, knowing that life elsewhere has managed to endure. The implications could even inspire us to better care for our own planet, recognizing Earth as a rare and cherished environment that has nurtured us for millennia. In the end, the search for extraterrestrial life is not merely about finding biological evidence. It is a philosophical, ethical, and existential journey. Each question raised, whether about contamination, communication, or coexistence, serves as a reflection of our hopes, fears, and aspirations as a species. The quest drives us to look beyond our world and, in doing so, to consider who we are in relation to the vastness of the cosmos.
James Webb, often described as the successor to the Hubble Space Telescope, has a unique set of instruments and capabilities designed to examine the universe with unprecedented clarity and range. Unlike Hubble, which observes in the visible and ultraviolet wavelengths, the Webb telescope primarily works in the infrared spectrum, allowing it to peer through dust clouds and capture detailed images of distant objects. This makes James Webb particularly well-suited for the search of alien life. And now, after nearly 3 years of operation, astronomers are using the observatory to look for life on thousands of newly discovered planets. The TRAPPIST-1 system, located about 40 light-years away, has become one of Webb's prime targets due to its 7 Earth-sized planets orbiting a cool dwarf star. 3 of these planets are located within the star's habitable zone, the range of distances where temperatures are just right for liquid water to exist. James Webb has been gathering data on the atmospheres of these planets, and preliminary results are intriguing. Early analyses suggest that several of these planets might have atmospheres containing gases like carbon dioxide, a crucial ingredient for organic molecules. In particular, TRAPPIST-1e, one of the planets in the habitable zone, shows signs of an atmosphere that may be capable of supporting life. Webb's ability to identify specific molecules has provided tantalizing hints, although scientists caution that more data is needed to make definitive conclusions. If signs of oxygen, methane, or even other complex molecules are detected, it could provide some of the most compelling evidence yet that TRAPPIST-1e might host some form of life. Closer to our solar system, Proxima b, an exoplanet orbiting within the habitable zone of the red dwarf star Proxima Centauri, has also captured the attention of astronomers. Located just over 4 light-years away, Proxima b is among the closest known exoplanets with potential for habitability. James Webb's advanced spectrometers have been pointed at Proxima b to gather atmospheric data. Although red dwarfs like Proxima Centauri are known for their frequent and intense stellar flares, which could strip away a planet's atmosphere, recent observations suggest that Proxima b might still retain its atmosphere. Fascinatingly, when focusing on Proxima b, the Webb telescope has detected an unusual, flickering light pattern on Proxima b. Scientists believe this mysterious light would be the city light that could theoretically indicate artificial illumination, possibly from a technologically advanced civilization. If true, Webb's finding would mark a groundbreaking discovery, potentially sparking a new era of exoplanetary science focused on the search for life. While smaller, rocky exoplanets are considered more likely candidates for hosting life as we know it, James Webb has also focused on larger gas giants and their moons. These gas giants, located in various star systems, often have complex atmospheric chemistries that, while likely unsuitable for life on the planets themselves, could hold clues to interesting chemistry and processes. In particular, Webb has captured high-resolution images and data on exoplanets with thick atmospheres, such as WASP-96b. Observations of this giant gas exoplanet's atmosphere revealed the presence of water vapor, clouds, and even a pattern of changing temperatures across the atmosphere. Such details are not only visually stunning, but also scientifically terrifying in their implications, as they reveal how radically different and dynamic exoplanetary weather can be. Perhaps even more intriguing, these findings open up questions about the moons orbiting giant exoplanets, much like Jupiter's moon Europa or Saturn's moon Enceladus. Both of these moons in our own solar system are icy, with subsurface oceans that could harbor microbial life. With James Webb's ability to study the atmospheres of exoplanets, researchers hope it may one day be able to detect signs of similar moons around other giant planets. Moons that may hold liquid water beneath their icy crusts. In the latest discovery, the telescope once again requires scientists to rethink our understanding of the universe. Is discovery, a cloud of carbon in a distant and compact galaxy as it appeared just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. The results have been accepted for publication in the journal Astronomy and Astrophysics, and a preprint version can be found on RFI. As co-author, Roberto Maiolino, a professor of experimental astrophysics at the Kavli Institute for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang. But we've found that carbon formed much earlier. It might even be the oldest metal of all." Astronomers classify elements heavier than hydrogen and helium as metals. That's because, aside from hydrogen and trace amounts of lithium, these elements were forged inside the fiery furnaces of stars and distributed throughout the universe by star explosions called supernovas. This process of heavy element production and seeding was once thought to take many star lifetimes before elements heavy enough to form planets were widely available. But new discovery made by James Webb has challenged this preconception. What James Webb found in the remote galaxy known as GS-Z12b, which was 100,000 times less massive than the Milky Way, were traces of oxygen and neon mixed with a strong signal of carbon. Exactly how carbon could have formed so early in the universe's life is unclear, although it could be due to stars collapsing with less energy than initially thought, according to the researchers. As carbon would have formed in the star's outer shells, this could have enabled it to escape and seed the early universe sooner than expected, instead of being sucked inside the black holes formed from the collapsing stars. That means it's not necessarily true that life must have evolved much later in the universe. Perhaps life emerged much earlier. Perhaps somewhere, under some conditions we might even consider too exotic for life. There are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. At that point, it simply becomes a game of hide and seek. Where is everybody? Why haven't we made first contact with aliens yet? This question is known today as the Fermi paradox, and it has had astrobiologists and other scientists scratching their heads for ages. First off, if we want to understand how the universe makes intelligent life, we have to consider two things. First, we have to consider the steps that needed to occur in order to bring about our own existence. And then we need to think about ways that intelligent life could arise in circumstances that differ from our own, and to make sure, wherever possible, that we're doing it in as quantitatively accurate a fashion as possible. We also have to make sure that we don't make unfounded assumptions or fall for any one of a number of logical fallacies, like conflating absence of evidence with evidence of absence, or the post hoc ergo propter hoc fallacy. It's also important to learn how not to estimate what's out there. There are two all too common mistakes that people, even the most brilliant of scientists, make when considering this question. One is that they make point estimates akin to, "We may not know this parameter, so here's what we estimate it to be," which is relatively meaningless. If you're going to make such an estimate, it's only meaningful if you include an uncertainty range, a set of error bars, or some other likelihood predictor. There's an enormous difference between saying that you estimate the odds of something to be 1 in 100 with a 10% uncertainty, a 1,000% uncertainty, or a two-tailed uncertainty where it could be as high as 1 in 10, but there could be no lower limit at all. However, the other mistake that people make is perhaps the most common of all when it comes to attempting to answer the Fermi paradox: making use of the Drake equation. The Drake equation yields many interesting lessons, and when it was first put forth, it was a monumental achievement from a scientific perspective. For the first time, it broke up a seemingly unknowable question of how many intelligent, spacefaring civilizations there are within our galaxy today into a series of smaller questions that we could conceive of solving one at a time. For example, we could measure or estimate things like the rate of star formation in the Milky Way, the share of stars that have planets, the average number of potentially life-supporting planets around stars with planets, the fraction of planets that could have life that actually wind up with life, the fraction of planets with life that go on to develop intelligent life, the fraction of intelligently inhabited planets that emit detectable signals, or the length of time that such civilizations continue to emit those signals. When you multiply all of those things, you'll wind up with an estimate for the number of active civilizations that we could potentially detect today. But immediately, we run into a few major problems. For one, we've measured the rate of star formation in the Milky Way, and we actually know it pretty well. Unfortunately, if you took that star formation rate and multiplied it by the age of the universe since the hot Big Bang, you'd wind up with almost no stars. You'd calculate that the Milky Way should have formed a total of around 10 billion stars over our cosmic history. I know that 10 billion probably sounds like a big number, but compared to the actual estimate for the number of stars in our galaxy, which is more like 400 billion, it's only 2 to 3%. Fortunately, it's easy to identify why this method of calculating how many stars we've formed, which you'd imagine would give you the total number of stars in the galaxy, is so thoroughly wrong-headed. The superficial reason is fairly obvious. The star formation rate is not constant over our cosmic history. In fact, we've come to understand that the universe was born without stars, which began forming during the first 200 million years or so. We've learned that star formation increased for the first 3 billion years of our cosmic history, reached a peak, and has been dropping ever since. Locally, we've probably experienced bursts of star formation when we've absorbed smaller satellite galaxies, and we might even be starting to experience another burst as the Magellanic Clouds and Andromeda exert their gravitational influence on the gas, dust, and other neutral matter within our own galaxy. But that's only the superficial reason why the Drake equation is problematic today. The deeper reason is that the Drake equation, when it was put forth, made an assumption about the universe that we now know is untrue. It assumed that the universe was eternal and static in time. As we learned only a few years after Frank Drake first proposed his equation, the universe doesn't exist in a steady state, where it's unchanging in time, but rather has evolved from a hot, dense, energetic, and rapidly expanding state, a hot Big Bang that occurred over a finite duration in our cosmic past. Instead, a much more productive route is to calculate the quantities we now can speak about with some level of certainty, and then move on to the great cosmic unknowns in as responsible a fashion as we can. Unlike the situation some 60 years ago, when the Drake equation was first proposed, we now have an excellent idea of what our universe is like, both in and beyond the Milky Way and the local group. We understand what the various populations of stars are that exist, and what sorts of steps need to occur to make heavy elements, rocky planets, and allow for the possibility of complex chemistry and important reactions, such as the formation of energy-storing molecules from nothing more than the ubiquitous building blocks and starlight. We've also learned a lot about the types and abundances of planets that exist around stars other than our own, exoplanets. As recently as 30 years ago, we were only discovering our very first planets around stars besides the Sun. At the end of 2021, we're closing in on a whopping 5,000 confirmed exoplanets. And sure, there are biases in our data. We're preferentially detecting the planets that are the easiest to detect. But we know how to account for those biases. Instead of needing to speculate about how many stars form, how many have planets, how many planets per system have the potential for life, we can actually utilize some excellent data. Here in our modern Milky Way, we already know how many stars there are, how those stars are divided into different populations, how many planets there are per star, how many of those planets have the right composition of elements to lead to complex chemistry, and how many of those planets have the potential for hosting life. On this front, it's actually straightforward to come up with a solid estimate for how many potentially habitable planets are in our galaxy. In fact, We can perform that calculation in a variety of ways, just to show the power of our set of knowledge. Of the approximately 400 billion stars in the Milky Way, about 80% are red dwarfs, just 18% are like the Sun, and only the 2% are too massive and short-lived to be interesting for life. As far as we can tell, there are about 5 to 10 planets per stellar system, with approximately 1 to 2 planets in what we call the habitable zone around each star. Of the planets that exist around Sun-like stars, we believe that 20% of them are Earth-like in terms of size. A greater percentage than that are terrestrial, around the more common red dwarf stars. If we assume conservatively that red dwarf systems are not habitable at all, but Sun-like systems are, we then derive an estimate for the number of potentially inhabited planets in the Milky Way, 21,600,000. It doesn't make sense to use so many significant figures. 20 billion is good enough. But also we have to remember that all of these numbers have uncertainties. There may be as few as 200 billion stars, half of our estimate. Some of the stars may be too low in metals, what astronomers call the heavy elements in the universe, for planets to support life, but the percentage is small, less than 10% for certain. Some stars might not have planets, but again, the percentage is small, less than 20% for certain. The habitable zone may be larger or narrower than we think. Tack another 33% uncertainty onto our estimate. And we haven't sampled the low end of the mass radius portion of the exoplanet population very well. Our estimate of 20% being Earth-like in size could go up or down, so it's reasonable to put a 25% uncertainty on that figure. All in all, there could reasonably be as few as 5 billion potentially habitable planets in the Milky Way, or perhaps as many as 50 billion. If red dwarf systems are potentially habitable as well, that number could increase tenfold. And at the same time, many of the things we've worried about in the past likely don't particularly matter one way or the other, such as whether a planet has a major moon or not. It could be nearly 100%, or 10%, or 1%, or 0.01%, or a 1 in a million chance that life arises from non-life. So if we rewound the clock and started Earth over again, how likely is it that life would have arisen and thrived here? Well, our ignorance is astounding. Similarly, once life does arise, how often does it get wiped out, versus how often does it endure for many billions of years? How frequently does it remain in a relatively simple state, unable to develop complexity, differentiation, multicellularity, or sexual reproduction? How often, even after billions of years, does it actually begin to look like life on Earth at the start of the Cambrian explosion? Again, we have no knowledge at all about how this might work. If you estimated that it occurred 10% of the time, that's reasonable. But so is 90% of the time. So is 0.001% of the time. Without observational or experimental evidence to point us in the right direction, we're simply deluding ourselves if we make a strong assertion. Furthermore, we know that after life on Earth became complex, differentiated, multicellular, and sexually reproductive, it still took more than 500 million years for a species to arise that would become technologically advanced, and that was likely just the result of random chance. How often does that occur? Does it make sense to represent this probability in percentages, or is this such a rare event that it's like winning the Powerball lottery 5 times in a row? Furthermore, how long does that technologically sophisticated life endure? Does it ever become a multi-planet or even an interstellar civilization, or is the progression from technologically advanced to extinct a relatively rapid one? At this point, our uncertainties are so large that it's eminently reasonable that not only might human beings be the only intelligent life in the Milky Way, but in the entire observable universe, which likely contains more than 1 trillion times as many stars as our own galaxy. We can confidently say, give or take, that there are perhaps 20 billion Earth-sized planets made of similar elements to our own world, at the right distance from their parent star to have liquid water on their surface, assuming an Earth-like atmosphere as well. But of those worlds, how many of them have life? It could be most of them, many of them, or only a tiny fraction. Of the ones with life, how many of them develop complex, differentiated, intelligent, and technologically advanced life? Before we even start asking questions about longevity, colonization, or machine-based life, we should admit, with a non-negligible probability, the most obvious resolution to the Fermi paradox. The reason we haven't made first contact with intelligent, technologically advanced, and spacefaring alien civilizations is because there are none. In all the galaxy, and perhaps even in all the universe, we really may be alone. Without evidence to the contrary, we have every reason to keep looking and searching, but still no reason other than our own preferences to believe that other creatures, similar to humans, exist out there. While it may be incredibly fun to theorize a myriad of possible explanations as to why intelligent extraterrestrials might remain hidden from us, the simplest possibility, that they just aren't out there, should be the default hypothesis until proven otherwise. What's notable, in addition to upend what we know about life in the universe, James Webb is also providing science with a further gift. Detecting exoplanets used to be so difficult that scientists spotted the first black hole, detected the leftover radiation from the Big Bang, and took snapshots of countless distant galaxies before discovering the first planet beyond our solar system in 1992. Plenty of exoplanet astronomers began their careers before the field of exoplanet astronomy even existed. But now, astronomers have identified well over 5,000. And continue to find more. It could be most of them, many of them, or only a tiny fraction. Of the ones with life, how many of them develop complex, differentiated, intelligent, and technologically advanced life? Before we even start asking questions about longevity, colonization, or machine-based life, we should admit, with a non-negligible probability, the most obvious resolution to the Fermi paradox. The reason we haven't made first contact with intelligent, technologically advanced, and spacefaring alien civilizations is because there are none. In all the galaxy, and perhaps even in all the universe, we really may be alone. Without evidence to the contrary, we have every reason to keep looking and searching, but still no reason other than our own preferences to believe that other creatures similar to humans exist out there. While it may be incredibly fun to theorize a myriad of possible explanations as to why intelligent extraterrestrials might remain hidden from us, the simplest possibility, that they just aren't out there, should be the default hypothesis until proven otherwise. What's notable, in addition to upend what we know about life in the universe, James Webb is also providing science with a further gift. The telescope is sensitive to infrared wavelengths, where these traces are strongest, and has already detected water, carbon dioxide, methane, and more on other worlds. That means Webb's planned 10-year lifetime could reveal a lot, perhaps answering fundamental questions including what exoplanets are made of, how they form, and whether our solar system is an oddball within our galactic neighborhood. Here are 5 big planetary puzzles that scientists hope to solve with James Webb. 1. Why do some rocky planets have atmospheres and others don't? If a rocky planet is going to host life, it needs an atmosphere. But scientists still aren't sure what determines whether a rocky body can hold onto a gaseous outer shell. Astronomers are searching for what they call the cosmic shoreline, a conceptual dividing line that separates worlds with and without atmospheres. In 2017, scientists identified such a shoreline within our solar system, set by the balance between the amount of radiation a planet or moon receives from the sun and the strength of the world's surface gravity. Sunlight provides gas particles with the energy needed to escape from the upper atmosphere, while gravity holds atmospheric gases to the planet. To test whether this type of cosmic shoreline exists throughout the galaxy, scientists need to figure out which exoplanets have atmospheres and which don't. This question may sound incredibly basic, but it's only just now becoming possible to answer, thanks to James Webb. Renyu Hu, an astronomer at NASA's Jet Propulsion Laboratory in Pasadena, California, says he and colleagues have settled the atmosphere question for 55 Cancri e, a planet that orbits a sun-like star some 40 light-years from Earth. 55. Cancri e is a super-Earth, a bit bigger than Earth but much smaller than Neptune. In a paper published May 8 in Nature, Hu and colleagues present Webb's data suggesting that 55 Cancri e has an atmosphere of either carbon monoxide, carbon dioxide, or a mix of the two with nitrogen. It's the first detection of an atmosphere shrouding a terrestrial or rocky exoplanet. But scientists are pessimistic about the existence of atmospheres on the other rocky worlds James Webb is observing, specifically those orbiting M-dwarf stars. These small, dim stars are easiest for James Webb to see. They also tend to spew bursts of atmosphere stripping radiation more often than stars like our Sun. So some scientists doubt that rocky planets around these stars can hold on to atmospheres. According to James Webb observations of LHS 3844b, a super-Earth orbiting such a star, the planet is almost certainly a bare rock. Webb's observations of the planets TRAPPIST-1b and TRAPPIST-1c, which orbit the M-dwarf TRAPPIST-1, suggest that these planets are bare too. But it's also possible that they could have very thin atmospheres, says astronomer Elsa Ducrot of the Paris Observatory. Follow-up work with James Webb will help settle the question. As scientists use the observatory to identify more examples of rocky planets with and without atmospheres, our understanding of the cosmic shoreline can be put to the test. 2. What is exoplanet geology like? Discovering exoplanets without atmospheres also will allow astronomers to study something impossible to probe directly before James Webb: exoplanet geology. Scientists plan to use James Webb to look for the chemical fingerprints of specific rocks in the infrared light cast by the rocky, airless super-Earth LHS 3844b. Learning what the planet's surface is made of would be a powerful clue about the planet's geologic history and ongoing processes. Finding signs of granite would be especially intriguing. Granite is a common rock on Earth that forms from recycled and remelted rock. On Earth, this process depends in part on plate tectonics. But beyond Earth, granite appears to be vanishingly rare, probably because plate tectonics is too. Right now, there's no more evidence for plate tectonics on other worlds than there is for alien life. Thus, finding granite-like rock on an exoplanet would be a major discovery. 3. What are rocky exoplanets made of? While James Webb will help astronomers learn about the surfaces of exoplanets, it also might offer a glimpse at their geologic guts thanks to a particularly extreme type of terrestrial world. Hotter than scorched Mercury, lava worlds orbit so close to their stars that their years are best measured in hours, not days or months. This proximity causes the planets to become tidally locked, meaning the same side of the planet always faces its sun. As a result, one hemisphere freezes in endless night while the other's rocky surface melts into lava. The magma oceans on the day sides of lava planets offer about as close to a window into the interior of a planet as astronomers could hope to find. Gases escaping from the magma might give clues to the composition of the planet's deep interior. And learning what planets are made of can tell astronomers a lot about how these bodies form, and whether their compositions and histories are similar to or different from the way rocky planets form in our solar system. 4. Sub-Neptunes are the most common planets in our galaxy. What are they? While what we know about Earth, Mercury, and Mars can help astronomers imagine what alien rocky planets are like, the most common type of planet in our galaxy can't be found in our solar system: UB Neptunes. So named because the planet's radii are just a bit smaller than Neptune's, seem to be everywhere scientists look. But scientists still know very little about these worlds. For example, are they gas giants, rocky planets, or something else entirely? Based on their masses and radii alone, sub-Neptunes might be miniature ice giants rich in ammonia, methane, and water, like Neptune and Uranus. But the same data could describe planets with very different structures, such as rocky cores wreathed in hydrogen and helium, or exotic water worlds made mostly of different forms of water, not necessarily liquid. Using James Webb, scientists plan to study the atmospheres of sub-Neptunes to distinguish between these possibilities. Webb's observations of the sub-Neptune K2-18b made headlines last year after researchers detected carbon dioxide and methane, but no ammonia, an expected component of gas planets, in its atmosphere. The team interpreted this gas mix as evidence for a water world, since ammonia dissolves easily in water and would get trapped in an ocean if it were there. But other researchers think the same data could fit a Neptune-like composition with a thick gas envelope over a rocky core. A definitive answer will require follow-up observations. 5. How do gas planets form? Despite having 4 gas giants in our solar system, scientists still aren't sure how these enormous worlds form and evolve. How do gaseous planets form? How do they evolve? And what are they made of? These are fundamental questions in planetary science that scientists still haven't answered. In particular, scientists want to know whether gas giants form where we find them, or whether they tend to wander over time, as they seem to have done in our solar system. Planets can wander due to gravitational interactions with other objects, including the disks of gas and dust that orbit young stars and provide the raw materials for planets. Gas planet migration can wreak gravitational havoc, knocking other planets out of their orbits and flinging around small bodies like comets and asteroids. The resulting chaos can have serious implications for the stability and potential habitability of smaller worlds. James Webb could provide astronomers with a vital clue to this mystery: the composition of gas giant atmospheres. The abundance of elements heavier than hydrogen and helium in gas giant atmospheres should depend on where the planet formed relative to its star. In general, the heavier the elements found in an atmosphere, the farther out the planet formed. Observing enough gas giant planets to start identifying trends and planets that buck them could reveal the general rules governing how these planets form and migrate. From the neighborhood to the edge of time, the James Webb Space Telescope challenged our understanding of the cosmos and showed the universe in a way no other telescope in the past could. And in a recent remarkable observation, the $10 billion Infrared Space Observatory has focused on Mercury, which should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. And now, by using powerful telescopes like James Webb, scientists have once again lifted the veil on the secrets of the planet, revealing Mercury is not what we think. Join us as we shed light on the most enduring mysteries of the innermost planet in our solar system. Mercury is the closest planet to the Sun, orbiting at an average distance of about 57.9 million kilometers. With a diameter of just 4,880 kilometers, it is the smallest planet in the solar system, slightly larger than Earth's moon. Despite its proximity to the Sun, Mercury's surface temperatures vary dramatically, ranging from scorching highs of 430 degrees during the day to freezing lows of 180 degrees at night. Mercury's orbit is highly eccentric, meaning it is not a perfect circle, but rather an elongated ellipse. This eccentricity, combined with its rapid orbital period of just 88 Earth days, leads to fascinating orbital dynamics that have intrigued astronomers for centuries. One of the most notable features of Mercury's orbit is its 3-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the Sun. The surface of Mercury is a stark, barren landscape, characterized by numerous impact craters, vast plains, and towering cliffs. The planet's surface bears the scars of a violent history, with craters ranging in size from tiny pits to massive basins hundreds of kilometers across. The largest of these is the Caloris Basin, a massive impact crater over 1,500 kilometers in diameter, formed by a colossal collision with an asteroid or comet billions of years ago. Mercury's surface is also home to a network of long, steep cliffs known as Lobat scarps. These scarps are thought to have formed as the planet's interior cooled and contracted, causing the crust to buckle and fracture. Some of these cliffs rise as high as 3 kilometers and stretch for hundreds of kilometers across the planet's surface. Despite its barren appearance, Mercury's surface is not entirely devoid of activity. Recent observations have revealed evidence of volcanic activity in the planet's past, with smooth plains and ancient lava flows suggesting that Mercury once had a more geologically active history. However, unlike Earth or Venus, Mercury's volcanic activity appears to have ceased billions of years ago, leaving behind a frozen, lifeless landscape. One of the most puzzling aspects of Mercury is its magnetic field. Mercury is the only terrestrial planet besides Earth to have a global magnetic field, although it is much weaker than Earth's. The existence of this magnetic field was first confirmed by NASA's Mariner 10 spacecraft in the 1970s, but its origin remains a mystery. A planet's magnetic field is typically generated by the motion of molten iron within its core, a process known as the dynamo effect. However, given Mercury's small size and proximity to the Sun, scientists were surprised to find that the planet still has an active dynamo. Theories suggest that Mercury's core may contain a higher proportion of iron than previously thought, or that the planet's core has a unique composition or structure that allows it to sustain a magnetic field. Adding to the mystery is the fact that Mercury's magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern hemisphere, a phenomenon that is not yet fully understood. Some scientists believe that this asymmetry may be due to variations in the planet's core or mantle, while others suggest that it could be a result of interactions between the magnetic field and the solar wind. What's more, unlike Earth, Mercury has no significant atmosphere. Instead, the planet is surrounded by an extremely thin layer of atoms known as an exosphere. This exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, and is constantly replenished by the solar wind, micrometeoroid impacts, and the release of volatile materials from the planet's surface. The existence of Mercury's exosphere was first confirmed by Mariner 10 and later studied in greater detail by NASA's Messenger spacecraft. The exosphere is so tenuous that it is barely detectable, with an atmospheric pressure less than a trillionth of Earth's. Despite its thinness, the exosphere plays a crucial role in the planet's interaction with the solar wind and the space environment. One of the most fascinating aspects of Mercury's exosphere is its dynamic nature. The atoms in the exosphere are constantly being stripped away by the solar wind, only to be replaced by new atoms from the surface. This continuous exchange of particles creates a delicate balance that can be easily disrupted by solar activity, leading to fluctuations in the composition and density of the exosphere. Mercury's most striking feature is its unusually large core, which makes up about 85% of the planet's radius. This core is believed to be composed primarily of iron, with smaller amounts of nickel and other elements. The sheer size of Mercury's core relative to its overall size is unique among the terrestrial planets and has led to much speculation about the planet's formation and history. One of the leading theories suggests that Mercury may have once been a much larger planet, with a thick, rocky mantle similar to Earth's. However, a giant impact early in the planet's history could have stripped away much of this mantle, leaving behind the dense metallic core we see today. This giant impact hypothesis is supported by the planet's high density and the relative scarcity of silicate materials on its surface. The core of Mercury is also thought to be partially molten, which may explain the planet's magnetic field. But the exact state of the core, whether it is completely liquid, partially solid, or something in between, remains an open question. Understanding the nature of Mercury's core could provide valuable insights into the formation and evolution of the inner planets in our solar system. However, given its proximity to the Sun and the extreme conditions on its surface, Mercury is a challenging planet to study. Mercury has been visited by only 2 spacecraft, NASA's Mariner 10 and Messenger missions. These missions have provided the bulk of our current knowledge about the planet, but what is really interesting about Mercury are the things that can't be seen. And now, thanks to incredible research efforts, scientists have finally given us some remarkable clues that could upend our understanding of this enigmatic world. In a groundbreaking revelation, scientists have discovered that Mercury, the innermost planet in our solar system, may harbor salt glaciers that could support life beneath its sun-scorched surface. This discovery is not only a significant leap in our understanding of the planet's geology, but also raises intriguing possibilities about the potential for life in environments once deemed inhospitable. The key to this new discovery lies in the data gathered by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger's suite of scientific instruments provided unprecedented insights into the planet's surface composition, magnetic field, and geological history. One of the most surprising findings from Messenger's mission was the detection of unusual surface features that suggested the presence of volatile substances, including water ice and salts. Researchers have long known that Mercury's poles contain deposits of water ice, trapped in permanently shadowed craters. These craters, located in the planet's polar regions, are shielded from the sun's harsh rays, allowing ice to accumulate and persist. However, the discovery of salt glaciers has added a new dimension to our understanding of Mercury's polar deposits. Analysis of Messenger's data revealed features that resemble glaciers on Earth, but with a twist. These so-called salt glaciers are formed from a mix of salts, such as sodium chloride and magnesium sulfate, and ice. The presence of these salt deposits suggests that, at some point in Mercury's history, liquid water may have been present on the planet's surface and subsequently evaporated, leaving behind these saline features. The formation of salt glaciers on Mercury involves several stages. First, volatile compounds such as water and various salts were likely present in the planet's crust. Over time, geological processes, including impacts and volcanic activity, would have brought these materials to the surface. When Mercury's surface temperatures fluctuated, especially in the shadowed regions near the poles, water ice could have formed and mixed with salts. The persistence of these salt glaciers is indicative of a complex climatic history. The planet's axial tilt is minimal, meaning that its poles receive very little direct sunlight. This, combined with the extremely low temperatures in the shadowed craters, has allowed these glaciers to remain relatively stable over geological timescales. The discovery of salt glaciers on Mercury prompts a re-evaluation of the planet's potential to support life. While the current conditions on Mercury are inhospitable to life as we know it, the presence of salts and ice raises the possibility that microbial life could exist in subsurface environments, similar to how life is hypothesized to survive beneath the icy crusts of moons like Europa and Enceladus. In addition to the presence of water ice and salts, the idea that Mercury once had a more temperate climate further fuels speculation about its potential for life. If liquid water was once stable on the surface, it opens up the possibility that life could have had a chance to develop during that period. Even if no evidence of life is found, these findings can provide valuable insights into the planet's geological history and the processes that shaped its surface. Another remarkable discovery: recent scientific research has unveiled a breathtaking possibility. Mercury might be hiding a treasure trove unlike anything we could have imagined, a diamond layer 15 kilometers thick. To understand how Mercury could host such an incredible deposit of diamonds, we first need to appreciate the planet's unique geological and environmental conditions. As told, Mercury is a planet of extremes. With temperatures fluctuating from a blistering 400 degrees during the day to a bone-chilling 180 degrees at night, the surface is subject to tremendous thermal stress. This temperature variation alone suggests that the planet's surface could be a breeding ground for complex chemical reactions. Additionally, Mercury's lack of a substantial atmosphere, unlike Earth's thick blanket of air, leaves it exposed to the harsh solar wind, a constant stream of charged particles from the sun. These factors combine to create an environment where only the toughest materials can endure. This leads us to the key ingredient in our story: carbon. We all know that carbon is an essential element in the formation of diamonds. Under the right conditions, extreme pressure and temperature, carbon atoms can rearrange themselves into a crystal structure, creating diamonds. On Earth, diamonds are formed deep within the mantle, where pressures are immense. They are then brought to the surface through volcanic eruptions encapsulated in kimberlite pipes. But Mercury's formation and evolution took a different path. Recent studies suggest that Mercury's formation was marked by a cataclysmic event. During the early days of the solar system, a massive impact stripped away much of Mercury's outer layers, leaving it with an unusually large core relative to its size. This event could have also compressed large amounts of carbon deep within the planet, creating conditions ripe for diamond formation. Unlike Earth, where tectonic activity and erosion constantly reshape the surface, Mercury's geological activity is limited. This means that any diamonds formed in its early history could have remained largely undisturbed, accumulating over billions of years to form a thick layer. The idea of a 15-kilometer thick diamond layer on Mercury might sound like science fiction, but it's grounded in solid scientific principles. If Mercury's early history did involve massive impacts and intense pressure, it's plausible that much of the planet's carbon was converted into diamonds. Over time, as Mercury cooled and solidified, these diamonds could have settled into a stable layer beneath the surface. Moreover, Mercury's proximity to the Sun means it has been bombarded with meteoroids for billions of years. These impacts could have further driven carbon deep into the planet's crust, adding to the growing diamond reservoir. Some scientists hypothesize that the upper crust of Mercury could be a mix of regolith and diamond-rich rock, with the diamonds concentrated at deeper levels where pressures were once highest. One might wonder how such an extraordinary claim could be substantiated. The challenge lies in the fact that Mercury is not an easy planet to study. Its proximity to the Sun makes it difficult for telescopes to observe, and sending spacecraft to Mercury presents its own set of challenges. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided a wealth of data that has since been analyzed to offer clues. Messenger's X-ray and gamma-ray spectrometers detected higher than expected levels of carbon on Mercury's surface, particularly in certain regions. This carbon, found in the form of graphite, could be the remnant of a once more extensive carbon layer that has since been weathered down by meteoroid impacts and solar wind. If graphite exists in significant quantities, it strengthens the case for diamonds lying beneath, as graphite and diamond are different forms of carbon. Moreover, the high radar reflectivity observed in some of Mercury's craters is another piece of evidence. Radar signals bounce back strongly from highly reflective surfaces, such as ice or metal. However, diamonds are also excellent reflectors of radar waves, meaning that these bright spots on Mercury's radar map could be hinting at diamond-rich areas. Regardless, to fully understand the implications of these discoveries, future missions to Mercury are crucial. The next major mission to Mercury is Bepi Colombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in October 2018, Bepi Colombo is currently en route to Mercury, with its arrival scheduled for December 2025. This mission is named after Giuseppe Bepi Colombo, an Italian scientist who first explained the relationship between Mercury's rotation and its orbit around the Sun. Bepi Colombo consists of two spacecraft, the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA. The two spacecraft will work in tandem to study Mercury's surface, interior, exosphere, and magnetosphere in unprecedented detail. The MPO will focus on the planet's surface and interior, mapping its topography, composition, and geological features, while the MMO will study the planet's magnetosphere and its interaction with the solar wind. One of the key objectives of Bepi Colombo is to build on the discoveries made by Messenger and answer some of the lingering questions about Mercury. For example, Bepi Colombo will investigate the origin of Mercury's magnetic field, which is much weaker than Earth's and is likely generated by a partially molten core. The mission will also study the composition of the planet's surface, including the mysterious hollows, bright, shallow depressions that appear to be unique to Mercury. In addition to its scientific goals, Bepi Colombo will test advanced technologies that could be used in future missions to Mercury and other planets. For example, the mission's solar electric propulsion system, which uses ionized xenon gas to generate thrust, could pave the way for more efficient space travel in the future. While Bepi Colombo represents the next significant step in Mercury exploration, scientists are already looking ahead to future missions that could build on its findings. These missions could take various forms, from orbiters and landers to sample return missions, and even human exploration. One of the most exciting prospects for future Mercury exploration is the idea of sending a lander to the planet's surface. A lander would provide an unprecedented opportunity to study Mercury's geology up close, analyze its surface composition, and conduct experiments that are not possible from orbit. For example, a lander could drill into the surface to study the planet's interior structure or deploy instruments to measure the heat flow from the interior to the surface, which could provide clues about the planet's thermal evolution. However, designing a lander capable of surviving Mercury's extreme conditions presents significant challenges. The lander would need to be equipped with a sophisticated thermal control system to protect it from the intense heat of the sun, as well as radiation-hardened electronics to withstand the harsh environment. Additionally, landing on Mercury's surface is no easy feat, given the planet's low gravity and lack of atmosphere, which makes it difficult to slow down the descent. Despite these challenges, there have been several proposals for Mercury lander missions. One such proposal is the Mercury Surface Element, also known as MSE, a concept developed by ESA as part of the Bepi Colombo mission. Although the MSE was ultimately not included in the mission, the concept could serve as the basis for future lander missions. Another proposal is the Mercury Lander Mission Concept, developed by NASA's Jet Propulsion Laboratory, or JPL, which envisions a lander equipped with a suite of scientific instruments to study the planet's surface and interior. Another ambitious goal for future Mercury exploration is the return of samples from the planet's surface to Earth. A sample return mission would allow scientists to conduct detailed analyses of Mercury's surface material in laboratories on Earth, providing insights that are not possible with remote sensing or in situ measurements. For example, scientists could study the isotopic composition of Mercury's rocks to learn more about the planet's formation and evolution, or search for traces of volatile elements that could shed light on the history of water on the planet. Designing a sample return mission to Mercury poses several technical challenges. The spacecraft would need to carry a lander capable of collecting samples, as well as a return vehicle to bring the samples back to Earth. The mission would also need to overcome the challenges of operating in Mercury's extreme environment, as well as the difficulties of launching a spacecraft from the planet's surface. Despite these challenges, advances in technology and lessons learned from previous sample return missions, such as NASA's OSIRIS-REx mission to the asteroid Bennu, could make a Mercury sample return mission feasible in the future. While human exploration of Mercury is still a distant prospect, it is not entirely out of the realm of possibility. Advances in space technology, such as nuclear thermal propulsion and advanced life support systems, could one day make it possible for humans to visit Mercury and conduct scientific research on the planet's surface. Human missions to Mercury would likely be similar in scope to the Apollo missions to the Moon, with astronauts landing on the surface for short durations and conducting experiments before returning to Earth. Human exploration of Mercury would offer several unique opportunities for scientific research. For example, astronauts could conduct geological surveys of the planet's surface, study its magnetic field and interaction with the solar wind, and search for signs of past or present water. Additionally, human missions to Mercury could serve as a stepping stone for future exploration of other planets in the inner solar system, such as Venus or Mars. The future missions to Mercury have the potential to revolutionize our understanding of the planet and its place in the solar system. By studying Mercury's surface, interior, atmosphere, and magnetosphere in greater detail, scientists hope to answer key questions about the planet's formation and evolution, its geological history, and its interaction with the Sun. One of the key scientific objectives of future Mercury missions is to understand the planet's unique composition. Mercury has a much higher metal content than any other planet in the solar system, with a large iron core that makes up about 85% of its radius. This unusual composition has led scientists to propose several theories about Mercury's formation, including the possibility that the planet was once much larger and lost much of its outer layers in a giant impact. Future missions could provide the data needed to test these theories and determine the true origin of Mercury's composition. Another important objective is to study Mercury's magnetic field and its interaction with the solar wind. Unlike Earth, Mercury's magnetic field is weak and highly variable, with frequent reconnection events that create intense bursts of radiation near the planet's surface. By studying these phenomena in greater detail, scientists hope to gain insights into the dynamics of planetary magnetic fields and their role in protecting planets from solar radiation. Future missions could also shed light on the history of water on Mercury. Although the planet is thought to be too hot for liquid water to exist on its surface, MESSENGER discovered evidence of water ice in permanently shadowed craters at the poles. Bepi Colombo and future missions could study these ice deposits in greater detail, potentially revealing clues about the sources of water in the inner solar system and the history of volatiles on Mercury. Finally, future missions to Mercury could help answer fundamental questions about the formation and evolution of the solar system, and by extension, offer clues about the conditions that led to the formation of Earth and other terrestrial planets. One of the most intriguing aspects of Mercury is its unusually high metal content. The planet has an iron-rich core that accounts for about 85% of its radius, which is proportionally much larger than Earth's core. This composition suggests that Mercury experienced a different formation and evolutionary history compared to the other terrestrial planets. Understanding why Mercury is so metal-rich could shed light on the processes that influenced planetary formation in the early solar system. There are several hypotheses about Mercury's high metal content. One theory suggests that Mercury might have formed from material that was metal-rich from the beginning, possibly as a result of the Sun's early influence. Another hypothesis proposes that Mercury originally had a silicate-rich mantle similar to Earth's, but a massive impact during its formation stripped away much of this mantle, leaving behind a metal-rich core. Studying Mercury in detail could help scientists determine which of these scenarios is more accurate, providing insights into the conditions that existed in the inner solar system during its formation. Mercury is the only other terrestrial planet besides Earth that has a significant magnetic field, although it is much weaker than Earth's. The presence of this magnetic field suggests that Mercury has a partially molten outer core, which generates the field through the dynamo effect. By studying Mercury's magnetic field, scientists can learn more about the planet's core dynamics and how its magnetic field has evolved over time. Understanding Mercury's magnetic field could also provide clues about the early magnetic history of Earth. Earth's magnetic field is crucial for protecting our planet from solar and cosmic radiation, making it a key factor in the development and sustenance of life. By comparing Earth's magnetic field with Mercury's, scientists can gain a better understanding of the factors that influence magnetic field generation in terrestrial planets and how these fields evolve. This knowledge could also help scientists predict the future behavior of Earth's magnetic field, which is currently weakening. Mercury's surface is heavily cratered, similar to the Moon, but it also has unique features such as large cliffs or lobate scarps that run for hundreds of kilometers. These scarps are thought to have formed as Mercury's core cooled and contracted, causing the planet's surface to shrink and buckle. The presence of these scarps suggests that Mercury's geological history is still active, albeit at a much slower rate than on Earth. Studying Mercury's surface features can provide insights into the planet's geological history and the processes that have shaped its surface over billions of years. For instance, understanding the formation of lobate scarps can help scientists learn more about the thermal evolution of Mercury's core and mantle. This, in turn, can offer clues about the thermal histories of other terrestrial planets, including Earth. Mercury also has regions known as smooth plains, which are believed to be the result of ancient volcanic activity. The presence of these plains suggests that Mercury had a more geologically active past than previously thought. By studying the volcanic history of Mercury, scientists can learn more about the planet's internal heat generation and how it has changed over time. This information could be valuable for understanding the volcanic history of Earth and other terrestrial planets, as well as the role of volcanism in planetary evolution. Mercury has a tenuous atmosphere, or exosphere, composed mainly of hydrogen, helium, oxygen, sodium, and potassium. Unlike Earth's thick atmosphere, Mercury's exosphere is constantly being replenished by particles from the solar wind, surface interactions, and outgassing from the planet's interior. Studying Mercury's exosphere can provide valuable information about the interactions between the solar wind and planetary surfaces. The study of Mercury's exosphere is particularly important because it offers a unique opportunity to observe how a planet's surface and atmosphere interact with the solar wind. Since Mercury is so close to the Sun, it experiences much stronger solar wind conditions than Earth. By understanding how Mercury's exosphere responds to these conditions, scientists can gain insights into the processes that shape planetary atmospheres in general. This knowledge can also be applied to Earth, helping scientists better understand how our planet's atmosphere interacts with the solar wind, and how this interaction has influenced Earth's evolution. Mercury's unique characteristics challenge many existing models of planetary formation. Traditional models suggest that terrestrial planets formed from the gradual accumulation of planetesimals in the protoplanetary disk. However, Mercury's high metal content, weak magnetic field, and unusual surface features suggest that its formation involved processes that are not fully explained by these models. Studying Mercury in greater detail can help scientists refine these models and develop new theories about planetary formation. For example, understanding why Mercury has such a large iron core relative to its size could provide insights into the role of giant impacts in planetary formation. Similarly, studying Mercury's magnetic field and geological history can help scientists develop more accurate models of how terrestrial planets evolve over time. Mercury offers a unique opportunity for comparative planetology, the study of planets by comparing their properties and histories. By comparing Mercury with Earth, scientists can identify similarities and differences that provide insights into the process that shaped both planets. For instance, both Mercury and Earth have metallic cores and magnetic fields, but the differences in their sizes, compositions, and geological histories can help scientists understand the factors that influence planetary evolution. One key area of comparative planetology is understanding the role of size in planetary evolution. Mercury is much smaller than Earth, which has significant implications for its thermal evolution, magnetic field generation, and geological activity. By studying these differences, scientists can learn more about how a planet's size influences its evolution and what this might mean for Earth. Another area of interest is the study of planetary atmospheres. While Earth has a thick atmosphere that supports life, Mercury's exosphere is extremely thin and constantly influenced by the solar wind. Comparing these two atmospheres can provide insights into the factors that determine atmospheric retention and composition, which are crucial for understanding the conditions necessary for life. Mercury's proximity to the Sun and its unique characteristics make it a valuable target for studying the early solar system's evolution. The planet's high metal content, weak magnetic field, and unusual surface features suggest that it has experienced processes that are not fully understood and that may have been more common in the early solar system. By studying Mercury, scientists can gain insights into the processes that influence the formation and evolution of the solar system as a whole. For example, understanding Mercury's formation and evolution could provide clues about the distribution of materials in the protoplanetary disk, the role of giant impacts in planetary formation, and the thermal histories of terrestrial planets. These insights could also help scientists better understand the conditions that led to the formation of Earth and other habitable planets. In short, while Mercury is a small planet with a big story to tell, its unique characteristics make it a key target for understanding the formation and evolution of the solar system, including Earth. By studying Mercury's composition, magnetic field, geological history, and exosphere, scientists can gain valuable insights into the processes that shaped our planetary neighborhood. These insights can help refine existing models of planetary formation and evolution, providing a clearer picture of how Earth and other terrestrial planets came to be. As we continue to explore Mercury, we are likely to uncover even more secrets about the early solar system and the forces that shape the world we live on today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.